Hi guys, come back to the Physics 145, next chapter, chapter 5. Chapter 5 will be work, energy, and power. Okay, work, energy, and power. So first one, we look at work done. Okay, work done. So what is work done? We actually look at one of the example in vector. Okay, so work done or work done is defined to be the dot product of the force and the displacement, okay, of an object. Okay, dot product. Okay, the dot product. So work done has a symbol W is equal to the F dot S, and in vector, dot product is actually a function that produces a scalar value. So dot product, this one will give us Fs cosine theta. So that is a formula that you need to know. So theta is actually the angle between the force and the F. So for the force and the displacement. So for example, if you have a object, okay, an object on a surface, okay, object on a surface, let's assume a smooth surface first, and you have a force and an angle theta, okay, theta, and when you apply the force, the object move a displacement s. The object move from here to here. So since the object is moving horizontal, your force is making an angle theta all the time with the horizontal line. And at the same time, this theta is also the angle between the F and the S. So our work done is calculated based on the F, the component here. Look at this component. Okay, the component of this force, which is parallel with the displacement. In this case, is the one parallel with the surface, horizontal surface. So our work done is F parallel multiplied by the displacement. But your F parallel is equal to F cosine theta multiplied by S. So finally you have Fs cosine theta. Okay. So this is one way in understanding where the formula comes from. Okay. So your work done is also can be defined to be the product of the force in the component in the direction of the S with the direction of the S, okay, with the displacement S. So this is normally the form 4, form 5 definition, because form 4, form 5 they didn't study the dot product. Alright, so that is our work done. So what's the unit of the work done? The unit of the work done is Fs. Okay, so the F Newton meter. Okay, Newton meter. So Newton meter is also the same as joule. Okay, this one is joule. Okay, joule. So that is our first one for work done. So we look at example of work done. Example 1 for work done. Split this one into two lines. So example for work done. Let's say you have a object on a smooth surface. Okay, so when I say smooth surface, that means your friction is equal to 0. So let's assume the object is pulled with a displacement of 50 meter by a force F of 100 Newton and an angle theta of 30 degree. Alright, so the mass can be given also, but the mass is not important when you come to a smooth surface. So the mass, let's say, is 5 kilogram. So calculate the work done. Okay, calculate the work done by the force F. You have to specify work done by whom. It can be work done by the friction, work done by the gravity, and so on. Okay, so the work done here will be W is equal to F dot S. Okay, F dot S or Fs cosine theta. So the F is 100 Newton and the displacement is 50 meter and the angle is 30 degree. Okay, so we have this 5,000 times cosine 30 degree. Right, so it gives us 4330 joule. Okay, 4330 joule. So that is positive because what? Because the work done is actively by the force F. So another question is, if I ask, calculate the work done by the block. Okay, because the block is being pulled, so that means the work is the block is not doing any work. It is being pulled. If the external force is doing a positive work by this much, the block will have this much of work done on it. So that means the work done by the block is equal to negative. Okay, the work done, this one is the work done by the force, this is the work done by the block itself. Because it is being pulled, so the work done is a negative of the active work done by the force F, which is negative 4330 joule. Right? By assuming no losses. Okay, assuming no losses. So that is how, if you are asked about this type of question, work done by the external force or work done by the block itself. Okay, so if you're asked to calculate the work done by the block, you simply calculate the work done by the force and then convert it to a negative value. Alright, unless a block will move by itself for no obvious reason. Well, that is something very spooky. Okay, now example number 2. Now we put in some friction. See what happens next. Okay, example 2, same block. Okay, same scenario, except now you have friction. Okay, object also being displaced 50 meter by a force F of 100 Newton and an angle theta of 30 degree, and then there is a friction F of 20 Newton. Okay, 20 Newton. Alright, so what? Calculate. Number 1, work done by F. Number B, work done by friction. And C, the total work done on the block. Okay, the total work done on the block. So that is the question that we have. Alright, work done by the force and work done by the friction and also work done by the block. So first we look at work done by the force F. So we can cover this one up. Okay, assume that the friction is not there yet, because later we're going to cover this one up and look at what happened to friction. Okay, now method 1. This is our method because we got 2 methods in solving this problem. Method 1, A, we calculate the work done by the force F. The formula is F dot S. So it gives us Fs cosine theta, and the theta is the angle between the F and the S, which is still 30 degree. So that means the value will be exactly the same like this one. Cosine 30, we'll just simply copy that value, 4330 joule. Okay, no problem with that. So that is our A. Now B. B, we want to draw that diagram again one more time, just to show that only the friction and the displacement. Now I will put them in blue color. Now this is our displacement. The object moves in that direction with a displacement of 50 meter under the frictional force of 20 Newton. Now if you look at that diagram, your displacement, which is a vector pointing to the right, your friction is also a vector pointing to the left. If I connect them, the the angle between them, the angle between these two quantities, here to here, theta is now 180 degree. Can you see that? This one is 30 degree. Now imagine that you flip this force this much up to here, so the angle between them is 180 degree. Alright, so now we can still use the same formula to calculate the work done by the friction, which is F dot S. Now instead of big F, now we have small f, and again the formula is the same, Fs cosine theta. Now the theta is between the friction and the displacement. Our friction is 20 Newton, displacement is still the same, but the cosine theta is 180. Okay, cosine theta is 180. So your cosine 180 give you -1. So -1, so that means multiply by this, 2 times 5, you got 10, so altogether you have 1000 joule. But because of cosine 180 give you -1, so you have a -1000 joule. Means that when the object is being pulled along to the right hand side, it lost 1000 joule to overcome the friction. Okay, to overcome the friction. So this one will affect the total work done. Just now the total work done on this block is 4330. So now the total work done on the block, we have to sum it up. W total is a W work done by the force F, big F, and plus the work done by the friction. So we have 4330 plus -1000, so we have 3330 joule. So you can see that in the same situation, if you have friction involved, the work done on the object will finally become smaller. The value is about 1000 different because of the friction. Okay, so that is our method 1. Okay, our method 1. Method 2 is straightforward. Okay, it's straightforward. So our method 2, okay, is like this. You need to find the net force first. Okay, the net force. The net force here is this component. Okay, our component, our F component, in this case, this one. Okay, F parallel minus the friction. So F parallel is a surface minus the friction. So what do we have here? We have this. We have 100 cosine 30 minus 20. So we have this force. Okay, we have this force. So it is 100. Oh, sorry, 100 cosine 30, which is 80 plus 86. Okay, and then minus 20. So now we have this much. Okay, 66.60. So it is 66.6 Newton. Now our work done will be the net force multiplied by our displacement, which is 66.6 times 50. See what do we have? This 66.6 times 50 Newton. So we have answer 330 joule. Okay, same answer. Except this one, you are not following the A, the B, and the C. You calculate one go. Okay, you calculate one go. So I would encourage you to use the first method because it's more detailed. If question asks ABC, definitely you have to use this method. But let's say question say calculate the total work done on the block, then you can use this method or you can use the method here. Okay, but I prefer this method myself now because it's more detailed. In case you got one wrong, you can have marks for the other. If this one you have one wrong, bye bye, sayonara to your marks. Okay, so that is our work done. All right, so these are page 1. Now our page, our next one will be after work done is energy. Okay, our energy. So there are two types of energy that you need to know under this part, this chapter here, 5.1. Energy. So our energy, the first one, okay, our first energy we're talking about is the kinetic energy. Okay, kinetic energy. The symbol I use here will be very much simple. E stands for energy, and then the K stands for the kinetic. So we have kinetic energy, EK. Later on we use other symbol. Okay. Now, our kinetic energy normally related to an object that is moving. Okay. but we also need to know the mass of the object and then the velocity of the object. So the formula for kinetic energy, Ek, is given by this, half m magnitude of the velocity, because velocity is a vector quantity. So we take the magnitude, it becomes the speed, half mv, the speed square. Okay, so that is the formula for our kinetic energy. Okay, so the larger the object, the more massive the object, the more the kinetic energy, and the more it can do damage. Or maybe the object is small, but because of the speed is very high. For example, bullets maybe just like 10 gram, 20 gram, or 50 gram, but it's travel at, let's say, at if you're talking about rifle, maybe it's about, well, more than 300, maybe 400 meter per second. If that one pass through your head, it's going to shatter like a watermelon. Okay, so that one is depending on two things here. But imagine an asteroid coming from the sky hit the earth. It have a very high speed and also very large mass, maybe the mass of a mountain. So if it drop one in Kuching, the size of the mountain like that, 1 kilometer across, there'll be no more Kuching. Kuching will become history. So a few thousand years later, people talk about Kuching, so it become a ancient archaeological site. Okay, so that is kinetic energy. Well, energy generally have unit of Newton meter or joule. As long as it is energy, don't care whether sound energy, light energy, potential, kinetic, magnetic, nuclear, they are all the same. They have the unit of joule. But in a higher level of physics, when it comes to nuclear energy, we have some other unit that is more convenient. Okay, electron volt, for example. Okay, EV, small e, big V. Those are the unit used more conveniently in chemical reaction and also in nuclear reaction. Okay, so it's not in our syllabus here. So that's number one. Number two is our gravitational potential energy. So the symbol I use is EP because of gravitational potential energy. Okay, some books might use this symbol, you see. Some book might use for kinetic energy is K, and then the potential is U. You can also use that one. It's a more high level of physics they use. Like for example, in photoelectric effect, they use a symbol K. Gravitational law, Newton's gravitational law, that one they use a big U. Well, you might look more powerful when you use a symbol that people use. Okay, now the potential, gravitational potential energy is related to height, how high the object goes. Okay, with a mass m under the influence of gravitational acceleration. Let's say the center of mass of the object is at the distance h. Okay, at the distance h from the ground level. This is the ground level. So the gravitational potential energy is given by this formula, mgh. Okay, mgh. So that means the higher you go, the more your gravitational potential energy. The larger your mass, the larger is your gravitational potential energy. And then the larger the g value, the larger is your gravitational force. Okay, gravitational potential energy. For example, I compare same mass, you put them at the same height, one on the earth, one on the moon. Moon has smaller gravitational potential acceleration. So even though the same mass put at the same height, on the surface of the moon, the object will have less gravitational potential energy, because the gravity g on the moon is only 1/6. That means 6 times less than the gravitational acceleration of the earth. All right, so that is the two types of energy that you need to learn under this chapter number 5. So what is the purpose of this one? Okay, so we come back to the purpose. That means why we only need to know about kinetic energy and gravitational potential energy. Well, these two energy are always together. We call them mechanical energy. Okay, mechanical energy. So now this is under 5, sorry, this one energy is 5.2. should be 5.2 already, sorry, 5.2. So our 5.3, I call them mechanical energy. Okay, so our mechanical energy, the symbol I use would be E. Okay, E. So mechanical energy E is equal to the kinetic plus our potential. They're always together. Okay, so when they are together, you combine them, they are always a constant. So that means we can apply this one in the in what we call the law of conservation of energy. Okay, but other than that, okay, we can actually combine, right, this one with the work done. So come to 5.4, we call this one work energy theorem. Okay, work energy theorem or work energy principle. So our work energy theorem states that, okay, so our work energy theorem, in exam you cannot use this one. This one is for me. See, lecturer got more power than you. So work energy theorem, okay, states that, the work done, or the work done on a system is equal to the change in energy of the system. Now, that work done definitely will refer to WFS, but the change in energy here, the change in energy, the delta, okay, we write down the formula first for this work energy theorem. The work done on the system is equal to the change in energy, alright? So your change in energy can be the change in energy of kinetic energy or the change in energy of the potential energy, gravitational potential energy, either one of them, okay? Or even can be combination of one of them, okay? So that is our formula to relate the change in energy and the work done, alright? So that is our work energy theorem. Okay, and then the next one, our 5.5, is the law of conservation of energy. Okay, law of conservation of energy. Okay, what does this law state? That it states that the total energy, okay, the total energy is always a constant, okay, at any point, okay, at any point of interest. Point of interest means the point that we want to study, okay, so that means it is always a constant. So that means your mechanical energy is always a constant, which is Ek plus Ep, which is equal to K, and it's always equal a constant, alright? So that is the law of conservation of energy. It is very important when we try to solve problem involving roller coaster, okay, roller coaster ride. For example, you have a roller coaster move like this, okay. So now let's say we have a few points here, our point A, and then the lowest point, point B, and then the medium point C. Now, if you look at these few locations, if point B is the lowest one, point A is at a certain height, and point C also at a certain height. Let's say this is HA, this is HC, and HB is equal to 0. Now, when I release the object, let's say the object initially is rolling down. You release, so that means the object released down. That one is the VA. And by the time it reaches here, it moves with a velocity VB. And by the time it reaches here, it moves with a velocity VC. Now, according to the law of conservation of energy, okay, according to the law of conservation of energy, what we have is this. The total mechanical energy at A must equal to the total mechanical energy at B and also at C. So that means your kinetic energy at A plus the potential energy at A must equal to the kinetic energy at B plus the potential energy at B, and also must equal to kinetic energy at C plus the potential energy at C. This one must stay. Assume that the surface here is smooth. Okay, so normally in your exam paper, your question, it will involve only 2 points at a time. Okay, for example, you are given here and you are asked to find the velocity at VB. This one not there. Or you are given B and C, find any one of them, and then maybe between A and C. That is what happened. So we can use this phenomena. Let's say between, okay, example, between A and C. What's the relationship between them? We know that it must be this one and this one, right? So we have kinetic energy at A plus the potential energy at A must equal to the kinetic energy at C and plus the potential energy at C. So that means I can use this. Half mVA squared plus mGHA must equal to half mVC squared plus mGHC. See, that is the meaning of the law of conservation of energy. All right. So most of the time we're using two location, 2 point of interest here, and you might start with this one and then followed by this one, and most of the time we cancel the mass because it's the same object that moving around. So by cancelling the mass, okay, you have a simpler equation. All right, so that is the law of conservation of energy. That is what it is talking about. And the last one for this chapter is 5.6 is power. Okay, so energy transform or work changes or work done. If you divide that value by time, it gives us power. Power is how much work is done per unit time, or you can also say that power is equal to the change of energy per unit time. Two definition, but we have three formula for power. First one, okay, first one, our definition for first one is the rate of work done. So that means power is equal to W over T. Or number two, we have the rates of transform of energy. It can be any form of energy, which is E over T. It can also like kinetic energy over time, gravitational potential energy over time. Any energy changes per unit time, that one is the power. And the third one, of course, we already have one formula, two formula, and our third formula is actually from here. Okay, so the third formula is the power is the product of force and velocity. Okay, how is it? P is equal to W over T, but your work done is Fs over Fs, right? So we take out the F and then we have S over T. This is displacement. Displacement over time is velocity. So it is Fv. So you see you have third formula. Alright. So these are the formula that you need to know. Alright. So that is our the fifth chapter. Chapter number 5. So this is our page number 2. Okay, after this we're going to look at example. Okay, example of our this chapter. Alright. Okay, we look at example 1. Oh, I think example on work done already, right? Oh, sorry, example on work done already. That's example 1. So now we look at example 2. Example 2. We don't go and specifically calculate the kinetic energy or potential energy of object because that will be too simple for you. we will start with the work energy theorem. Okay, work energy theorem. Okay, let's start with something like this. A car, okay, a car moving with velocity 20 meter per second is accelerated to 25 meter per second in a time interval of, let's say, 10 seconds. Okay, 10 seconds. All right, so now calculate A, the work done. Okay, the work done by the engine. Okay, work done by engine. We assume the efficiency of the engine is 100%. Of course, they're not true, but for our calculation, it is 100%. And then B, the power of the engine. All right. So that is our example number 2. Okay. So we start by we need to know the mass of the car also. Given the mass of car equal to 400 kilogram. Okay, 400 kilogram. So our first one, A, the work done. Okay, because we don't have force, we cannot use Fs. Okay, and we also don't have displacement. But we know one thing. According to the work energy theorem, we know that the work done is equal to the change in energy. In this case, change in kinetic energy. Okay, change in kinetic energy. So our changes in kinetic energy is this: half mv squared minus half mu squared. This is a final velocity, which is 25, and this is an initial, which is 20. So the mass we already know, so we can take out this half m v squared minus u squared, easier for our calculation. This is 400 mass, and then this is 25 squared minus 20 squared. Okay, so 25 squared minus 20 squared, we have this multiplied by 400 and then divide by 2. We have 45,000 joule. Okay, 45,000 joule for the work done, okay, by the engine. Next one is B, power. Okay, power P. But since we already have work done, so we can use this one. So this work done, 45,000 joule, happen in a time of only 10 seconds. Okay, 10 seconds. All right. So our answer is 4,500 joule per second, or this is equivalent to 4,500 watts. Okay, 4,500 watts. Oh, forgot to give you the unit for the power. The unit for power is equal to joule per second of watts. W-A-T-T. Alright, so that is our power. Alright, now next one, example number 3. Now example number 3, we are talking about things that is being moved up. Okay, so let's assume this is the horizontal ground. Okay, and then we have ladder. Okay, we have ladder. Well, that is okay, our ladder is not really that consistent. Okay, as long as you can reach the top there by the wall. Okay, now the height of the ladder, let's say is 3 meter. Okay, 3 meters. Now there is a boy. Okay, there's a boy. Okay, one of you lah. So now this boy is running up the stairs. Okay, so a boy. Why very sexist, huh? All the time the boy, okay lah, boy or girl lah. Okay, a boy or a girl walks up a flight of stairs, okay, a flight of stairs case, or just a flight of stairs, okay, in a time of, let's say, 3.0 seconds, okay, 3.0 seconds. Calculate, okay, the power of the boy or the girl if his or her mass is 65 kg. Alright, so that is the question. That is the question. So we know that, you see that walks up, normally we assume no acceleration. Okay, no acceleration. So this guy or this boy or girls here, so it's going to move from low location to high, and the difference in the height is 3 meters. We are not calculating this one. We are not calculating this one. If you want to calculating according to this movement, you have to use work done one by one. You have to calculate how much force this guy is giving his feet on the steps to push himself or herself up one by one. That one will be tedious, a lot of calculation involved. So that's why work energy theorem is very easy to use. But here is quite easy. We use change of energy. So our change of energy, our power will be equal to energy changes over time. But our energy changes here is the energy changes for potential energy. Okay. So what we have here is what? Potential energy here is mgh. Okay. Final minus mgh initial. The initial height is 0. So that means the whole term here will become 0 afterwards. Divide by the time, which is 3 seconds. So we know that this is equal to 0 already. So now we need the mass, 65. Our gravity, 9.81. And then the height is 3 meter. Divide by 3. So our answer is 3 cancel 3. We have 65 multiplied 9.81. We have 638 joule per second. Okay, or watt. Okay, or watt. Alright, so that is our example number 3. Alright, example number 3. Next one, example number 4. Example number 4 will involve a car that is moving, okay, with a constant velocity. Okay, so this question is really very simple. So a car or a van, always a car, boring also. A van, okay, a van move with a constant velocity of 30 meters per second when the engine is supplying a constant power of 35 kilowatts. Okay, 35 kilowatts. All right, calculate the average force produced. Calculate the average force produced. Okay, so see, you got velocity, you got power, you want to calculate force. Definitely we are using the third equation here. Okay, this one, right? So our equation will be P is equal to FB. The power is 35 kilowatts, another 30 is equal to force multiplied by velocity. So our average force here is 35,000 divided by 30. So we have 1167 Newton of force. But this force is our average force. It can be more, a little bit, smaller, a little bit. Alright. So that is the examples for chapter number 5. So you keep updated, okay, for your chapter number 6. And remember to do your exercise, the one I just posted to you a few days ago. Alright, so thank you.